Hello everyone. So, today we will solve few example problems on convection in internal flows. So, first let us summarize that the Nusselt number for thermally and hydrodynamically fully developed flow you can see for different cross sectional pipe. So, this is your Nusselt numbers for fully developed laminar flow in tubes of differing cross sections. So, you can see here for circular cross section we have already derived Nusselt number for this particular case. If you see, if it is a constant wall heat flux, then it is 4.36, and if it is constant wall temperature, then 3.66. These we have not derived, but you can see that for a square cross sectional duct, the Nusselt number for constant wall heat flux it is 3.61, and for constant wall temperature it is 2.98. Similarly, you see for a rectangular cross sectional channel where B by A is 1.43. Okay. So, B is here, A. So, for this particular case, for constant wall heat flux boundary condition, the Nusselt number is 3.73, and for constant wall temperature 3.08. If you change the B A by A ratio, you can see the Nusselt number for two different wall conditions. Now, if it is a parallel plate, okay, so that means B by A is infinity. So, in this particular case already we have derived the Nusselt number for constant wall heat flux it is 8.23, and for constant wall temperature it is 7.54. And if it is a triangular cross sectional channel, then Nusselt number is 3 for constant wall heat flux and 2.35 for constant wall temperature. And you see that the Nusselt number we have defined based on the hydraulic diameter. So, first let us take this problem. Water flows through a tube with a mean velocity of 0.2 meter per second. The mean inlet and outlet temperatures are 20 degree centigrade and 80 degree centigrade respectively. The inside diameter of the tube is 0.5 centimeter. The surface is heated with uniform heat flux of 0.6 watt per centimeter square. Determine the maximum surface temperature. So, you can see it is uniform wall heat flux boundary condition. So, your wall temperature will vary in axial direction, and where it is expected to be maximum at the outlet, right. So, TW will be maximum. Now, first for this problem first we have to find what is the Reynolds number. If the Reynolds number is in laminar zone and if it is a fully developed flow for both thermally and hydrodynamically, then we know what is the Nusselt number. So, for this particular case you know that the Nusselt number is 4.364. Okay. So, first let us calculate the Reynolds number and the developing length or entrance length. So, properties of water at film temperature 50 degree centigrade. Okay. So, it is the average temperature. So, Cp, K, rho, nu and Prandtl number are given. So, you calculate first from here the Reynolds number. Okay. So, this is your U mean into D divided by nu. So, um is given because it is 0.2 meter per second. So, it is 0.2 into the diameter is 0.5 centimeter. So, it is 0.005, okay, divided by 0.5537 into 10 to the power minus 6. So, this is the nu. So, if you calculate it will come as 1806, and as Reynolds number is less than 2300, the flow is laminar. Now, we need to find the length of the tube, that is also unknown, and we have to find whether the exit is in developing zone or not. So, we have to find the developing length first, so that if it is a fully developed flow, then we can use Nusselt number is equal to 4.364. How do you calculate the length of the pipe? So, you use this conservation of energy between the inlet and outlet. Okay. You can see, so if Q double prime W is at the wall, the heat flux is supplied. So, total heat transfer is your pi dl is the heat transfer area into Q double prime W is equal to m dot Cp into Tmo minus Tmi. Okay. So, length you can calculate as m dot Cp into Tmo minus Tmi divided by pi d Q double prime W. You can see here all the parameters are known except m dot. So, m dot you have to calculate. So, the mass flow rate m dot you can calculate as rho into u bar into cross sectional area. Okay. So, what is that? Rho u bar or u mean you can write. Okay. So, u m and pi d square by 4. Okay. So, m dot you will get. So, what is rho? Rho is 988, velocity is 0.2 into pi d square 0.005 square by 4. Okay. So, m dot you will get as 0.00388 kg per second. Now, you put it here, then you find the length. Okay. So, it will be 0.00388, Cp is 4182 and Tmo is 80 degree centigrade minus Tmi is 20 degree centigrade divided by pi d is 0.005 and heat flux is 0.6 watt per centimeter square. So, you write it as in watt per meter square. So, it will be 0.6 into 10 to the power 4. Okay. So, length of the pipe is 10.33 meter. So, this length we have calculated. Now, let us calculate the entrance length. For laminar flow in a tube, the hydrodynamic and thermal lengths are given by LH by dE entrance length, hydrodynamic entrance length. So, it is Ch into Reynolds number d. Okay. And for thermal developing length, it is Ct Prandtl number into Red. So, you know that from table. Okay, that Ch, this coefficient is 0.056 and Ct is 0.043 for this circular cross sectional pipe. So, if you put it here and Reynolds number is 1806, Prandtl number is 3.57. Let us calculate the LH. So, LH will be Ch 0.056 into D 0.005, Reynolds number 1806. So, it will be 0.506 meter and LT will be Ct is 0.043 into 0.005, Prandtl number is 3.57, Reynolds number is 1806. Okay. So, thermal entrance length is 1.386 meter. So, you can see the length of the pipe is 10.33 meter and we want to calculate the maximum surface temperature which will occur at the exit. Okay. So, at L is equal to 10.33 meter and hydrodynamic entrance length and thermal entrance length are much less than the length of the tube. So, here it will be fully developed. So, you can see it is a laminar flow and it is a fully developed flow. So, Nusselt number for this particular case will be 4.364. Okay. So, now let us calculate the heat transfer coefficient from here. So, you can see your H d by K is 4.364. So, your it is average heat transfer coefficient and local heat transfer coefficient are same because it is a constant value. So, it is 4.364. Thermal conductivity, okay. So, it is 0.6405 divided by diameter 0.005. So, your heat transfer coefficient is 559 watt per meter square degree centigrade. Okay. So, now we have calculated the heat transfer coefficient, but we need to calculate the maximum temperature. So, now you do the heat flux, okay, at the outlet. Okay. So, Q double prime W you can write as H heat transfer coefficient into T W at x equal to L minus your mean temperature. So, your mean temperature is known, that is TMO at the outlet. Okay. So, from here T W at x equal to L you will be able to calculate as TMO plus Q double prime W by H. Okay. So, what is TMO? TMO is your 80 degree centigrade plus Q double prime W, it is 6000, okay, 0.6 into 10 to the power 4 divided by 559. So, if you calculate it you will get 90.7 degree centigrade. Okay. So, your maximum temperature at the outlet, okay, is 90.7 degree centigrade. So, let us take the next problem. Air flows with a mean velocity of 2 meter per second through a tube of diameter 1 centimeter. The mean temperature of a given section in the fully developed region is 35 degree centigrade. The surface of the tube is maintained at a uniform temperature of 130 degree centigrade. Determine the length of the tube section needed to raise the mean temperature to 105 degree centigrade. So, you can see in this particular case it is a case for uniform wall temperature, okay, and it is a fully developed region, already it is told, okay, your mean temperature at a given section, okay, it is given as 35 degree centigrade. Now, we have to calculate the length of the tube section where the mean temperature is to be raised to 105 degree centigrade. Okay. So, first we have to calculate, the Reynolds number and we have to check whether it is laminar zone or not. So, if it is a laminar flow and it is a fully developed already told in the problem, so we can use the Nusselt number, okay, for a fully developed condition. So, Reynolds number, first let us calculate. So, d by nu. So, properties of air at TF film temperature at 70 degree centigrade, Cp, K, rho, nu and Prandtl number are given. So, is 2, diameter is 1 centimeter, so it is 0.01 meter and nu is this one. Okay. So, 19.9 into 10 to the power minus 6, okay. This is equal to 1005. So, as Reynolds number is less than 2300, the flow is laminar. Okay. So, the flow is laminar and it is a fully developed region already stated in the problem. So, we can use the Nusselt number based on diameter for this uniform wall temperature is 3.657. Okay. We can calculate the H, okay, as 3.657 into K. What is the K value? K value is here 0.02922 divided by D, right. Nusselt number is H d by K. So, it will divided by D is 1 centimeter means 0.01. meter. So, it will be 10.69 watt per meter square degree centigrade. Okay. So, now let us calculate the mass flow rate. Okay. So, mass flow rate m dot is rho um into area, cross sectional area. So, rho is 1.0287 into mean velocity is 2 meter per second, cross sectional area is pi by 4 into d square, okay, 0.01 square. So, this if you calculate you will get 0.001616 kg per second, okay. And the perimeter is pi d, right. So, it will be pi into 0.01 is equal to 0.03142 meter. Now, from the energy balance analysis we have calculated the dTm by dx. If you remember, the expression is dTm by dx is equal to q double prime w p by m dot Cp. Okay. So, this you know. So, now q double prime w you can write in terms of heat transfer coefficient. So, if you write that, so what is q double prime w? Q double prime w is H into T w minus T m, right. So, this you can write H T w minus T m, okay. Perimeter we have calculated divided by m dot into Cp. Okay. So, now if you see that dTm by Tw minus Tm, we can write P by m dot Cp into H. Okay. So, if you integrate it, okay, from inlet to the outlet, so you will get ln Tw minus Tmo divided by Tw minus Tmi is equal to minus PL m dot Cp 1 by L, okay, 0 to L H dx. So, what it is? If you remember, this is nothing but your H bar, okay, and in this case it is H bar is equal to H. So, that we have calculated. So, this value is known. So, from here you will be able to calculate the length L as m dot Cp divided by P into, so this is your H, okay, and ln Tw minus Tmi divided by Tw minus Tmo. So, this we have reversed because this minus sign I have taken care here, okay. So, if you put all the values here, so you can see m dot is 0.0001616 into Cp is this one 1008.7 divided by P, perimeter we have calculated as 0.03142 into H we have calculated as 10.69, okay. ln Tw is 130 minus 35 divided by 130 minus 105, okay. So, if you calculate this you will get 0.65 meter. So, the length of the tube section needed to raise the mean temperature to 105 degree centigrade is 0.65 meter. Let us discuss about the next problem. Steam condensing on the outer surface of a thin walled circular tube of diameter d is equal to 50 mm and length L is 6 meter maintains a uniform outer surface temperature of 100 degree centigrade. Water flows through tube at a rate of m dot is equal to 0.25 kg per second and its inlet and outlet temperatures are 15 degree centigrade and 57 degree centigrade respectively. What is the average convection coefficient associated with the water flow? So, you can see this is the tube. So, inert surface is maintained at 100 degree centigrade and water is flowing through it, m dot is equal to 0.25 kg per second and inlet mean temperature is 15 degree centigrade, outlet mean temperature is 57 degree centigrade, L is 6 meter. So, now we have to calculate the average heat transfer coefficient. So, properties of water at Tf is equal to 36 degree centigrade is this one Cp we need for this calculation. So, now if you see that we know heat flux q double prime W as H T W minus T m. Okay. So, we have calculated just now T m by dt m by dx as q double prime W P by m dot C p. Okay. So, this is equal to H T W minus T m, that is your q double prime W P divided by m dot C p. Okay. So, now dt m by T W minus T m if you write, and you can write it as minus P L divided by m dot C p 1 by L 0 to L H dx. So, as earlier problem, this represents your average heat transfer coefficient. Okay. So, from here you can see your H bar. Okay, after integration you can write H bar as m dot C p divided by P into L ln T W minus T m I divided by T W minus T m O. So, this we have already calculated in the last problem. Okay. There you calculated the L, in this particular case we are calculating the H bar. Okay. So, you put all the values. So, m dot is given 0.25 kg per second. So, 0.25 into Cp 4178, perimeter is pi d. So, pi into diameter is 50 millimeter. So, 50 into 10 to the power minus 3, and length is 6 meter. Okay. Ln wall temperature is 100 degree centigrade, inlet temperature is 15 degree centigrade, and outlet temperature is 57. So, 100 minus 57. Okay. So, if you calculate it, your H bar you will get 755 watt per meter square Kelvin. Okay. So, let us discuss about this problem. Water at 25 degree centigrade enters a pipe with constant wall heat flux q double prime W is equal to 1 kilowatt per meter square. The flow is hydrodynamically and thermally fully developed. The mass flow rate of water is m dot is equal to 0.01 kg per second, and the pipe radius r naught is 1 centimeter. Calculate Reynolds number, the heat transfer coefficient, and the difference between the local wall temperature and the local bulk mean temperature. The properties of water at 25 degree centigrade are given mu and k. Okay. So, this is a case of uniform wall heat flux boundary condition. So, for this particular case, first you calculate the Reynolds number. Okay. So, it is water. So, rho you know. So, your Reynolds number is rho u m d by mu. Okay. And mass flow rate is given m dot. So, you can calculate m dot is equal to rho u m into cross sectional area. So, what is rho u m? Rho u m is m dot by AC. M dot is 0.01 kg per second and AC is pi by 4 d square. So, or pi r square you just write. R naught is given 1 centimeter. So, pi r square. So, 0.01 square. So, this is your meter, 1 centimeter is 0.01 meter. So, you can see that your rho m is this one. Now, Reynolds number you can calculate 0.01 by pi 0.01 square into diameter is again 0.01 into 2 divided by mu 8.96 into 10 to the power minus 4. So, Reynolds number from here if you calculate you will get 710. Okay. So, this is your obviously less than 2300. So, the flow is laminar. So, as it is a laminar flow and in fully developed condition, Nusselt number for constant wall temperature boundary condition, as the flow is laminar and it is a fully developed flow. So, the Nusselt number for uniform wall heat flux boundary condition is 4.36. So, from here you can see Nusselt number is 4.364. So, from here you can calculate H as Nusselt number D into K divided by D. So, it will be 4.364 into K is given as 0.6109 divided by 0.01. So, if you calculate it you will get 133.3 watt per meter square, okay, Kelvin. Now, what is the difference between the local wall temperature and the local bulk mean temperature? So, we know Q double prime W as H into T W minus T M. Q double prime W is known, H we have found. So, you can calculate T W minus T M as Q double prime W by H. So, Q double prime W is 1 kilowatt per meter square. So, 1 into 10 to the power 3 watt per meter square divided by 133.3. So, you will get 7.5 Kelvin. So, you can see the difference between the local wall temperature and local bulk mean temperature is 7.5 Kelvin. So, now we will consider this problem. Consider a cylindrical rod heating element of length L and diameter D that is enclosed with a concentric tube. Water flows through the annular region between the rod and the tube at a rate m dot. The outer surface of the tube is insulated. Heat generation occurs within the rod and the volumetric generation rate is known to vary with a distance along the element. The variation is given by this relation. Okay. So, Q triple prime is the heat generation rate and per unit volume and Q naught triple prime is a constant. A convection coefficient H exists between the surface of the rod and the water. So, obtain an expression for the local heat flux and the total heat transfer rate from the heating element to the water. B. Obtain an expression for the axial variation of the bulk mean temperature of the water, and C. Obtain an expression for the axial variation of surface temperature of the rod. So, you can see the inside tube. So, this diameter D is shown. So, for this is the solid rod, okay, and it is the heat generating rod, okay, heating element, and for the flow is occurring in the annulus. So, you can see this is the space through which your fluid is flowing. Okay. So, obviously, you can see that if at a distance x, if you take a dx length, so you can see in this volume whatever heat is generated from this surface at a steady state, whatever it is leaving this surface, that is actually taken by the fluid. So, that energy balance we can do. So, you can see it will be just E dot G whatever is heat generated. So, that is the dq taken by the fluid, okay. And if at the inlet the mean temperature is Tm. So, Tm plus dTm. So, there is an increase in the mean temperature dTm, okay, and m dot is the mass flow rate. So, the energy balance you can see that E dot G is equal to dq from this elemental volume. So, Q triple prime is Q naught triple prime x by L square. So, you can see if you put it here E dot G. So, E dot G is Q triple prime into the volume. So, what is that? So, it will be q triple prime. What is the volume? Okay. So, if this is the length dx, so you can take as the cross sectional area, you can take average as pi d square by 4 into dx, okay, is equal to. So, dq is whatever q double prime, that a heat flux into pi d, okay, into dx. Okay. So, you can see the surface heat transfer surface is pi d into dx, through which actually this is going, and what is the heat is generated in the volume. So, this is the volume, right. So, this is the volume, d is the diameter. So, pi d square by 4 into dx. So, this is the volume of this heating element, okay, cylindrical rod. So, this volume is pi d square by 4 into dx. So, into q triple prime we will give you the total heat leaving the surface, and now the circumferential area through which your heat is transferred to the fluid, that area is pi d into dx. Okay. So, that is the heat transfer area, and the heat flux, if it is q double prime, then q double prime pi d into dx. Okay. So, what we will do now, you put this expression here, because q naught triple prime is constant, and we will integrate it from 0 to L. L is the length of the pipe, so x equal to 0 to x equal to L we will integrate. So, if you put this value, then we will write q naught triple prime 0 to L x square by L square pi d square by 4 into dx is equal to 0 to L q double prime pi d into dx. Okay. So, this is the expression. So, from here you can see what is q double prime. Q double prime is just q triple prime naught, okay, into x by L whole square. Okay. So, you will get d by 4. Okay. So, this is your local heat flux, okay, local heat flux. So, now if you calculate the total heat transfer rate, so the total heat transfer rate, what is that? So, q will be just, you need to integrate this q double prime pi d into dx. Okay. So, this into you have to integrate from 0 to L. Okay. So, q double prime is the local heat flux. So, what is the area? So, this is your pi d into dx. So, that is the heat transfer area, and that you need to integrate 0 to L. So, you can see q double prime pi d dx is nothing but this right hand side. So, now if you put this one only the left hand side, then you will get q triple prime 0 to L x square by L square pi d square by 4 into dx. Okay. So, if you carry out the integration, you will get q naught triple prime pi by 12, because x cube by 3. So, 3 into 4 12 and L cube. So, L cube by L square. So, you will get 1 L. Okay. So, d square into L. Okay. So, now you perform the energy balance in the control volume. So, performing the energy balance in the control volume. Okay. So, this is the control volume. Okay. So, whatever E dot G is generated. So, dq is taken by the fluid. So, you can see you will get m dot Cp dTm. Okay. dTm is the change in the mean temperature, right, dTm. Okay. So, m dot Cp dTm is equal to dq, okay, and dq is nothing but q double prime pi d into dx. So, you can write dTm by dx Okay. dTm by dx you can write as pi d by m dot Cp into q double prime, and q double prime if you remember. So, you can write q double prime is just this divided by pi d into dx. Okay. So, if you write that expression, so you will get pi d q naught triple prime x square d divided by 4 L square m dot Cp. Okay. Now, if you integrate it, okay, the mean temperature T m at x at inlet T m I is equal to pi d square by 4 q naught triple prime divided by m dot Cp. So, these are constant, you can take it outside the integral. So, it will be 0 to x x square by L square dx. So, your mean temperature variation you can see T m x is equal to T m I pi d square by 4 q naught triple prime by m dot Cp, and it will be x cube by 3 L square. Okay. So, we have found the mean temperature variation. Now, you have to find the wall temperature variation along the axial direction. Okay. So, that if you do this, so from Newton's law of cooling, you can write q double prime is equal to h into T w minus T m, right, and T m already we have found from this expression. So, T w you can write as T m plus q double prime by h. Okay. So, you can see you can write T w which is function of x, T m x you know. Okay. So, T m x is your T m I plus pi d square by 12 L square q naught triple prime by m dot Cp, then you have x cube and q double prime by h, right. So, q double prime if you write, so q double prime, so you can write as, so this expression. So, it will be q naught triple prime, okay, x square d divided by 4 L square. So, this is your q double prime and divided by h. Okay. So, you can see this is the expression of wall temperature variation along x. So, today we solved total 5 example problems. In most of the problem you have seen that we have considered fully developed flow both hydrodynamically and thermally, but before taking the Nusselt number for a fully developed condition, first you cross check what is the Reynolds number and the whether it is fully developed flow. If Reynolds number is less than 2300, then the laminar the flow is laminar, and if you see the entrance length and this entrance length is less than the required length of the pipe where you want to find the heat transfer coefficient or the heat flux, then you can use the Nusselt number expression for thermally and hydrodynamically fully developed laminar flow condition. So, you know that for uniform wall heat flux boundary condition, for flow through a pipe the Nusselt number is 4.364, and that we have used to calculate the heat transfer coefficient. In other case, from the energy balance, okay, you can calculate the heat transfer coefficient, okay, but that heat transfer coefficient obviously it is a local heat transfer coefficient, and after doing the integration you can calculate the average heat transfer coefficient, and these we have already studied in the initial lectures of these convection in internal flows. Also we have taken up one problem where inside the rod heat generation is taking place. Okay. So, and heat generation per unit volume we have considered, and that we have equated with the heat flux at the wall carried by the fluid. Okay. And at steady state, you know, whatever is heat is generated inside the heat generating element, that heat will be carried out by the fluid. So, with that energy balance, okay, we have used, and we have calculated the total heat transfer rate, and also we have done the energy balance in the fluid volume, where the mean temperature at inlet we have considered and mean temperature at the outlet we have considered. So, m dot Cp dTm, that is the fluid is carrying the energy, okay, equal to whatever the heat flux into the area heat has come from the heat generating body. Okay. So, that we have equated, and from that expression we have calculated the variation of mean temperature along the axial direction, and equating or using the Newton's law of cooling, we have calculated the variation of wall temperature in the axial direction. So, if you have seen that in last 3 modules we have solved several problems. Okay. Initially we considered thermally and hydrodynamically fully developed flow, because the calculation is easy, the analysis is easy, and also we started with the slug flow, where you have a constant uniform velocity, okay, um, and then we considered fully developed condition, where the velocity profile is parabolic, and also we considered thermally fully developed flow, where the non dimensional temperature phi does not change in the axial direction. Later we considered fully hydrodynamically fully developed flow, but thermally developing flow. Okay. So, for this particular case also we considered 2 different types of boundary conditions, constant wall heat flux and constant wall temperature boundary conditions. In each cases we found the expression of local Nusselt number and the average Nusselt number. However, we have not studied where it is a thermally and hydrodynamically developing flow. So, it is the analysis is more complicated. If you are interested, you can refer some books, okay, convection heat transfer book, and you can derive the Nusselt number for this particular case as a homework. Thank you.